Hello, welcome to Lesson 3, CE 3372 Water Systems Design. The topic is pressure pipe hydraulics, and this is largely a review of fluid mechanics principles, as well as possibly some new material when we discuss the creation and solution of pipeline network problems. We're going to review the hydraulics of closed conduits, in particular in the context of pipelines and networks, and we'll make heavy use of continuity and energy. Hydraulics is an applied science that deals with mechanical properties of fluids, and fluid mechanics is the theoretical foundation for everything today in this lesson. And in water systems, the working fluid is water. Some important characteristics is that water will move from higher to lower energy along the path of least resistance. And the term we had from fluid mechanics called head is the energy per unit weight of a fluid, and it represents the energy at a location in a fluid system, or in a water system, if you will, that liquid has. There's gravity flow systems where the change in elevation is what provides the working energy to move things from one location to another, as well as overcome friction. And then pressure flow is where the changes in pressure provides the required energy to move material from one location to another and or overcome friction. And pumps are the usual tool that are used to increase the energy to move to a higher elevation or over a barrier. The flow of water itself creates a frictional resistance, and so there's the loss of energy along a flow path, and the flow rate is related to the cross-sectional area and mean section velocity by the equation shown here, which says mean section velocity is discharge divided by cross-sectional flow area. If we look at two cross sections, A1 and A2, A1 is on the left, A2 is on the right. For continuity to be satisfied, the product of velocity 1 and A1 must equal the product of velocity 2 and A2. Hence, if we know the difference in areas, we know what the change in velocity will be. In this particular picture, as drawn, the velocity on the left side would be much smaller than on the right side. Basically, that's why we put nozzles on garden hoses to make them squirt better. When we get to a junction, so here's our junction right there. We have, I'm showing Q1 coming in, Q2 leaving, and Q3 leaving along those three pipes, and an additional component that's leaving, which is D. And this is the demand at the junction. And by convention, demand is positive leaving a network and negative going into a network. A negative demand would be like an injection. It's an unusual concept in pipeline simulation modeling, but not unheard of. So keep that in mind. So your demands in general will be positive. Continuity for the node. So continuity for this node is shown here by equation 3. It says that the continuity at the node is the sum of the inflows minus the outflows equals 0. Or Q1 minus Q2 minus Q3 minus D equals 0. Now usually we're going to write it as Q1 minus Q2 minus Q3 equals D. But this is probably the more rigorous way. Now the head loss along a pipe is given by an equation like this, which we know is the energy equation or modified Bernoulli's equation. And in that, these alpha terms were kinetic energy correction coefficients. We'll take them as having numerical value of 1. If there's a pump in a pipe, then that pump can add head. If there's a turbine, that can remove head. And then if there's always head loss, so that removes head. And the assumptions for application to a system is that we can approximate the pressure in the system with hydrostatic at both cross sections. The fluid's essentially incompressible, which means the density is constant across the cross-section, and the flow is steady. Everything here is for a steady flow. For unsteady flow in pipelines, that's a non-trivial complication and outside the scope of class. So let's examine this diagram really quickly. And so here we have a lower reservoir. We have a pump that provides energy to lift to an upper reservoir. Perhaps before this diagram, let's take a simpler look at a slightly different case. Okay, so let's suppose we have a tank here and a tank here. Tank on the left has water up to that height. Tank on the right has water up to that height. We have some datum here. And we're going to ultimately connect these tanks to a pipeline system. So let me go ahead and prepare the connections. Actually, I don't like that connection. Forget that. We're going to come right out at the bottom. But everything's closed. So we can measure to where the center line of that pipe is. This distance, call it Z1. This distance, call it Z2. If we look at the two instances on left and right, clearly the pressure at this location is going to be bigger than at that location. A way to visualize that is imagine you put your eyeball right by this and then punch a hole in that. This is going to come out faster and it's going to hurt you more than that one. It has a greater pressure, so P1 over rho G is the relationship of pressure, density, acceleration, gravitational acceleration to how deep the water is, P2 over rho G. Okay, so there's our two cases. Now if we move just outside, so we still have a Z1 at that location and a Z2 at that location. We're essentially in the same location, but there's no pipe between them. As soon as we connect a pipe, open the connection so that water can flow, if you'll pretend that the tank elevations don't change, then we know there'll be some discharge from left to right. And if we had a way to measure pressure here, it perhaps would go, let me do a little bit of a cheat here. Probably go up to here and up to here at these two locations. So let's call this one Z1 star. So P1 star over rho G, P2 star over rho G. And we could join those two pressures with a line, and if anywhere we measured in the system, at least at steady flow, this line would be the hydraulic grade line. It would be the height of elevation plus pressure anywhere in the system. Well, you'll notice that at the two reservoirs, the total head's quite a bit bigger, and the difference between the two is the V squared over 2G, which in this particular diagram is Q squared over 2G times A squared. So that's our first introduction to energy. And if we wrote the energy equation for the pipe, we'd have P1 star over rho G plus Z1 star plus V1 squared star over 2G equals P2 star over rho G plus Z2 star plus V2 star squared over 2G, and then plus any head loss going from 1 to 2. And what the head loss will impact is how these two lines reconnect into the reservoirs. Now in this diagram, these reservoirs are junctions. So there could be other pipes connected to them. And then this pipe is a link. And so if we were to write this equation in terms of the link, we would have head loss is equal to P1 minus P2 over rho G plus Z1 minus Z2, trying to keep everything grouped, plus V1 squared minus V2 over 2G. If it's constant diameter pipe, these velocities will probably be the same, and so the head loss will simply relate the difference in pressures and the difference in elevations to one another. Okay, so we'll have head loss equations for a link. And for junctions, we'll have continuity. And this will matter fairly heavily when we get to pipeline network analysis. So returning to this diagram, here we have our datum, in this case, which is set equal to the water level in the left reservoir. And here we have a water level in the right reservoir. We have this distance that I'm drawing, which will be called the static lift. And that's simply the difference in the two elevations. So whatever this pump right here has to do, it's got to at least generate the static lift, if nothing else, to keep the water from flowing back downhill. Now in this diagram, the water is being sucked up a short suction section into a pump. It's accelerated, which adds energy, so that just on the downstream of the discharge side of the pump, the energy goes to this elevation, and then it flows, as far as the energy world is concerned, downhill towards the reservoir. Now the actual water, of course, is moving uphill, but the energy, which is comprised of this pressure component plus this velocity component, is greater than the total energy at the receiving reservoir. Here at the supply reservoir, we see the energy is decreasing until it gets to the pump, and so the pump has a they're calling a suction lift component, plus there is a velocity head component. So going from the hydraulic grade line to the center line of the pump is called the pump suction pressure. That has an important property. And then there's the physical elevation that the pump is above the supply pool. And then on the downstream side, we've already discussed that it adds pressure. Velocity in this particular diagram doesn't seem to change, which would be indicative that the pipes on either side of the pump are the same diameter. And then here we have these intermediate standpipes showing where the hydraulic grade line is as we're moving in the system. We can apply the energy equation for this picture, and the amount of head the pump supplies is this line right here. And that head has to overcome the required static lift, which is Z2 minus Z1, as well as any frictional head losses in the system. In this particular case, H sub T is going to be 0. The hydraulic grade line is the line that represents the surface profile of the water flowing in a partially full pipe, which is not of interest yet, but is later in the semester. If the pipe is under pressure, then the hydraulic grade line rises to where a free surface would exist if there were a piezometer installed in the pipeline. And so here's the diagram showing a hydraulic grade line and then the energy grade line, which is determined in this diagram by a pitot tube, which captures both the static head as well as the dynamic component from the kinetic energy of the moving water. The energy grade line is the line that represents the elevation head. Flowing in a conduit, it's a sum of elevation, pressure, and velocity head. It's going to be above the hydraulic grade line at a distance equal to the velocity head. When we go the other direction in a turbine system, we still have energy grade lines and hydraulic grade lines, only in this case we're taking energy out. And here that equivalent height is being removed from the system and turned into electricity to run Las Vegas, Nevada, and make all the gambling machines go ding, 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 ding. You're a winner. This Okay, as an example, here's a fairly common problem. They had this, I think, in fluid mechanics. This is a case where we have two reservoirs that are connected by a pipe. We have the known change in pool elevation, and perhaps our goal is, so in this case, the goal is to estimate the discharge between the two reservoirs. We're told that the head loss is equal to 0.136 times the length times Q squared over pi squared G d to the 5th power, where d is 2 feet. Length is, let's see, 10,560 feet. And we're told it's a cast iron pipe, and so we'd look up the roughness height. For a cast iron pipe. And once we knew that, we could determine the discharge. So here's what we have, and we knew that the delta Z was 20 feet. And so now we want to write the picture we have is this. We have all the pieces, and if we look at the left side, we would have the total head here at the left is equal to the total head at the right plus the head loss. So we have 20 feet equals head loss, which is a function of Q, which is equal to 0.136 times the length times Q squared over pi squared G d to the 5th power. The only thing that's unknown is Q, so it wouldn't be too difficult to solve this equation for Q. And doing that, we would have, let's see, 20 feet times 2 to the 5th power times pi squared times G will be 32.2. divide by the length 10,560, divide by 0.136 equals q squared. And so now we would simply do the arithmetic. Can't do this unless I can find my calculator. There's my calculator. See, it calculates. 2 to the 5th should be 32 times 32.2 times pi times pi times 20 divide by 10560 divide by 0.136. So I get q squared equals 141.6 cubic feet per second squared, and you take the square root of that, is 11.9 cubic feet per second. Okay, that's a reasonably common problem. In this particular case, because the problem writer gave us the head loss equation, we're able to solve it directly. But this is a common enough problem. There's online resources to solve similar ones, and so let's take a look at those. If we go to the toolbox, we're going to look at flow between two reservoirs with no pumps, and this is the same problem. We're going to have to look up two values. We need to know the kinematic viscosity, and we'll need to know the sand roughness height. So let's first get the kinematic viscosity because that's the easiest. We go to liquid properties US, do it about 60 degrees. So the kinematic viscosity, I'm writing it down on the paper you can't see, is 1.22 times 10 to the minus 5th feet squared seconds. And now we know REG. We'll look up a roughness height for cast iron pipes. And let's see if it has a nice... Ooh, cool. Naturally, it's in millimeters. I don't want to do them in millimeters. I want them in English units. Dang it. There we go. Cast iron is 0.010 inches. We're going to divide that by 12 to get it into feet. So 0.01 divided by 12 is equal to 0.12383. So this is what we just looked up using the internet. And now we'll go back to our tool. Flow between two reservoirs. Okay, so our pool elevations, one's 120. We'll set these internal losses to 0 for the time being. Pipeline length is 10560. Pipeline diameter was 2 feet. Sand roughness height 0.00083. We just looked it up. Kinematic viscosity 1.22 E minus 0.05. And graviton acceleration 2.2. And we should get around, I think we'll get 11 something. And we get a calculated discharge of 11.89 cubic feet per second. Now the reason we get essentially the same answer is it's essentially the same problem. Now remember these other little loss terms, this inlet loss, fitting loss, exit loss, those were not included in our analysis. But that brings us into the concept of head loss models. So the one that we just used was Darcy-Weisbach, and we used actually the Jane equation when we did the online tool. There are other two in common use are HAZEN-Williams and Chezy-Manning. Chezy-Manning much less for pipeline systems. HAZEN-Williams is used throughout the United States for pressurized pipeline systems. Concepts are about the same. The numerical values of the different friction factors are different. And then there's fitting and minor losses. So we've just actually, we have this added head of a pump, which is not today's subject, but we also have the head loss model here. So Darcy-Weisbach, which you had back in fluid mechanics, head loss is proportional to length and velocity squared, inversely proportional cross-sectional area through the diameter, and the loss coefficient, that script F, depends on the Reynolds number and the roughness height. One way to do it that you did in fluid mechanics was using a Moody chart. There were three classical examples. The first one is here, pumping oil uphill. And what you would do is apply energy equation. Because it's constant diameter, the two velocity components cancel one another out, and all you have is static head to the left equals static head to the right plus head loss. Rearrange the equation, and then we can find the pressure drop. And what we need is a head loss model to handle the right-hand side here of equation 11. At the given flow rates, the Reynolds number is 85,000, and the roughness height, we look from Moody chart, in feet is 0.00085. We compute the roughness ratio, so we take the sand roughness height divided by the diameter for a ratio, and then that ratio determines which of these families of lines to use. One here is shown in teal. We enter with the Reynolds number, hit the teal line, read off the friction factor, and it was 0.024, and that gives us a head loss of 38 feet. Then to compute the pressure drop, we have to account for the elevation change, and that solves that problem. The next common one is discharge given head loss, diameter, and material. Very similar to what we just did with the two reservoirs. Apply Darcy-Weisbach directly. Compute the roughness height ratio. Make a computational table to do guessing. And with repeated guessing and updating, we come up with pipe discharge about 0.009 cubic feet per second. Now the modern equivalent of this guessing is iterative solving, and we'll see an example of that when we get to pipeline networks. We have nonlinear systems of equations. They have to be solved by iteration. Think of it as very clever guessing. Last example is to find the diameter given everything else. So here's a 600-foot iron pipe carrying water 20 degrees at 3 cubic feet per second. How big around does it have to be? And it tells us the pipe drops 60 feet in the direction of flow, and the desired change in pressure is 6 feet ahead. So we write the energy equation. We have the head loss model, and from that we know that the head loss needs to be about 66 feet. And we want to build a computation table. And so here we make a diameter of the guess, compute a Reynolds number, roughness height, friction factor, head loss divided by friction factor, and then when we multiply the two, we get the head loss term. And so 0.51 feet gives us the head loss of 63 feet, which is about as close as we'd be able to get. And so after 3 tries, the diameter is between 6 and 7 inches. Let me make a note of these because we can redo this problem using the online computer. So we have 600 feet long, 60 feet delta elevation, and we want 6 feet delta pressure, and we want to find the diameter. And it is wrought iron, so I'm pretty sure we're going to use the same 0.00083 feet. Okay, so the alternative is to use one of these equations. Both of these are given right here. They're also in the various reading materials. In this particular instance, we'll use the second one, and we have an online tool to implement it. So we'll go back here to the online tool, and we want diameter given head loss. Okay, so my only mistake is I forgot to get the discharge. 3 cubic feet per second. There we go. It's a lot easier now. Okay, so it's 3 cubic feet per second. 32.2 is gravitational acceleration. The head loss in feet was 66. We were told the pipe was 600 feet long. Roughness height 0.12383. And the kinematic viscosity we already looked up with 1.22 E minus 0.5. And we should get a diameter of about half a foot. And it computes the diameter of about 0.55 feet. And so that was the same problem that was done in the PowerPoint, done using the online tool. Okay, the online tool is to help us check our work. That's its purpose in life. So that particular online tool implemented this equation. We have some other online tools that will did one. I'll do example 2. I'll do example 2 using an online tool. So we have an 80-foot pipe, a half-inch diameter. We'll convert that into feet in a second. Head loss is 40 feet, and we want to know what Q is. And wrought iron pipe. Okay, so 0.5 divided by 12 is 0.041 feet, 0.041 feet, and now we have everything we need to do. We'll go ahead and go to our online toolkit. We want discharge given head loss. Value in diameter is 0.041. Gravitational acceleration 32.2. H is 40 feet. Pipeline length is 80 feet. Roughness height, we'll use the same one, 0.00083. Kinematic viscosity, we looked up already, 1.22 E minus 0.5. And it tells us that the computed discharge is 0.006 cubic feet per second. Let's see what we got here. Ours was 0.0009 cubic feet per second. And so probably the main difference is the roughness height. Let's repeat the online one with the same roughness height it was used here. Roughness height was 0.015. And now we get a discharge of 0.0084, which is pretty much the same value as doing it by hand many moons ago. We don't know the temperature, so I don't really know what the correct value of kinematic viscosity to be used. The point is, examples 1, 2, and 3 can all be done using these equations or the online calculator. I'm going to skip this part on how to build an online calculator. Pretty much that's more for different context, and we'll move on to the next head loss model called HAZEN-WILLIAMS. This one's for water only, and it assumes turbulent flow only, so the Reynolds number's got to be bigger than 4,000, and the loss coefficient, we look it up in a table. As a head loss equation, it looks like this, and the main difference is instead of the velocity being squared, it's to the 1.85 power. So it's close to a quadratic, but not quite. The 3.02 is a changes depending on whether you're in US customary or SI. I'm pretty sure this is US customary version. The SI is going to have a different number up front. We can write it in head loss form. We can convert it into discharge form. Here's an example of some C factors. This came from Engineering Toolbox. By all means, use the internet when you're doing these. And here's an example using HAZEN-WILLIAMS. Let's write down the parameters of the example so that I can do them using an online tool. So we have 72 inches, which is 6 feet, 10,000 foot pipe, 200 CFS. What's the head loss? Okay, we may not actually have and we're given that the C sub H is 100. So we could put that into the HAZEN-WILLIAMS formula and determine the head loss as shown here. Alternatively, we can try and see if there's something in the online toolkit on the off chance we're having to use it. Head loss in a pipe using HAZEN-WILLIAMS US customary. Here's the 3.02, and there's a table of C factors if you need them. Okay, loss coefficient for that example was 100. Diameter was 6 feet. The length was 10,000 feet, and the supplied discharge was 200 cubic feet per second. And so the computed head loss is 27 feet. And when we return to the PowerPoint, essentially the same number, 28 feet. Okay, the HAZEN-WILLIAMS is also presented as a velocity equation, and it usually uses the hydraulic radius rather than the explicit pipe diameter. The hydraulic radius is defined as the ratio of cross-sectional flow area to wetted perimeter. In a circular pipe that's full, it turns out that the hydraulic radius is 1/4 of the pipe's diameter. This diagram shows the area in green, and then the perimeter is this red curve right there. And the hydraulic radius is the ratio of those two. So for a pipeline that's full, the hydraulic radius is diameter divided by 4. In other conditions, that's no longer true. If it's not a circular pipe that's full, that's not true. The last one I want to look at is Chezy-Manning. In this case, frictional loss proportional to velocity squared in length, inversely proportional to cross-sectional area, but it's expressed as a hydraulic radius. And this loss coefficient called Manning's N depends on material and finish, and it gets looked up in a table, very much like HAZEN-WILLIAMS. Last component are the fitting losses, those losses at bends and inlets and outlets. So fittings, joints, elbows, inlets, outlets cause additional head losses. They're called minor because they occur over a short distance, not because they're particularly small. The commonly used loss model is the minor fitting loss head is equal to some constant multiplied by v squared over 2g. And in the case where a fitting changes diameter, we use the smaller diameter that produces the bigger velocity. Here's an example of some fittings for some different kinds of junctions. Here's a long radius, get the right one. Here's a flange long radius, 90 degree, versus a flange regular 90 degree. And so these long sweep elbows that you find at Lowe's for doing plumbing, they're to help herd the turd along down to the sewer system. There is measurable reduction in frictional loss coefficient. It's not big, but you start adding that up over enough pieces and it makes a big difference. Here's an example. What's the pressure drop across a valve with a nominal diameter of 8 centimeters, loss coefficient of 3.2 for this particular given flow rate. First, we'd write the minor loss equation and solve for the head loss, in this case 10.3 meters, and then convert the head loss into a pressure drop from rho g times the head loss is the change in pressure, and come up with basically 101 kilopascals in this example, about 1 atmosphere. That's pretty good pressure drop right there. All right, let's return to this diagram again. So we've now looked at the head loss model. There's minor losses at inlets, elbows, and exits, and those are all looked up, and we had that back in your fluid mechanics class. And then we have losses due to the different pipeline lengths. And so the minor losses plus the pipeline losses are all added together to come up with the head loss model. So now we have the energy equation going from location 1 to 2 is the pressure plus velocity plus elevation head at location 1 plus whatever the pump adds is equal to pressure plus velocity plus elevation head at location 2 plus the total head losses along the way. Next time we'll discuss things about pumps and system curves and some